Somewhere between 40 and 60% of Americans are taking a vitamin their body cannot fully use. Not because the label is lying, not because the supplement is fake, but because there is a single biochemical step, quiet, invisible, happening at the cellular level that their body is not completing. And without that step, the vitamin passes through, the deficiency continues, and the symptoms that have been accumulating for years keep getting attributed to everything except the actual cause. The signs don't arrive dramatically. They look like aging. They look like stress. They look like the predictable dimming that people in their 50s and 60s learn to accept, the fatigue that sleep doesn't fix, the mood that sits a register lower than it used to, the thinking that works against a resistance that wasn't there a decade ago. Doctors run panels, numbers come back in range, and the conversation moves on. Meanwhile, something foundational keeps running below capacity, quietly shaping the trajectory of the heart, the brain, and the nervous system in ways that won't fully announce themselves for years. There is a name for the process that's failing. There is a name for the genetic variant that makes it fail faster, one that roughly half the population carries without ever being tested for it. There is a specific marker in your blood that captures the cumulative damage of that failure with remarkable precision, predicting cardiovascular events and cognitive decline more accurately than cholesterol in some populations, and your last physical almost certainly didn't include it. And there is a form of the vitamin your body actually needs, one that bypasses the broken step entirely, sitting on the shelf next to the version that doesn't work, priced almost identically, with nothing on the label that explains the difference. What separates the two? Who actually needs the methylated form? And how would you know if you're one of them? What does a blood test that costs less than a copay reveal that years of standard blood work never captured? And what actually changes in the brain, in the cardiovascular system, in the texture of daily life, when the body finally gets what it's been missing? That's what this video is about. There's a question worth sitting with for a moment. Not a complicated one, but one that most people have never been asked. When was the last time you thought about what actually happens to a vitamin after you swallow it? Most of us don't. We read the label, we see the numbers, we trust that the capsule is doing its job. And for a lot of nutrients, that trust is reasonable. But the B vitamins, particularly B9 and B12, work differently than almost anything else you put in your body. They don't just get absorbed and used. They have to be converted, transformed, taken apart and rebuilt into something the body can actually work with. And that process, quiet, invisible, happening in the background of every cell, is where things can go wrong in ways that take years to show up on the surface. To understand why, it helps to step back and look at what the B vitamins actually are as a group. They're not one thing. The term B vitamins describes a family of 8 distinct water-soluble nutrients, each with its own role, its own pathway, its own relationship with the body. B1, B2, B3, B5, B6, B7, B9, B12. They share a category because they tend to work together, supporting energy metabolism, red blood cell production, nerve function, and the synthesis of DNA. But they're no more interchangeable than 8 different instruments in an orchestra. You can't replace one with another and expect the same result. Now, of those 8, 2 are doing something particularly critical for people over 50. B9, better known as folate, and B12, cobalamin. These two work in close partnership inside a biochemical process that most doctors don't explain and most patients never ask about. That process has a name, the methylation cycle. And it is, without exaggeration, one of the most important metabolic systems in the human body. But here's where the conventional advice starts to crack. For decades, the standard recommendation has been straightforward. If your B levels are low, supplement. If you're over a certain age, take B12. If you're pregnant or thinking about it, take folic acid. Clean, Simple, done. Except that the form these supplements come in matters enormously. And most of what's on the shelf, in the multivitamins, in the fortified cereals, is not the form your body is actually equipped to use directly. The version of B9 found in most supplements and nearly all fortified foods is called folic acid. It's synthetic. It was introduced in the 1940s, became the standard of care, and has been in the food supply ever since. The version that exists in whole foods, in leafy greens, in legumes, in liver, is called folate. Different structure, different behavior in the body, different journey through your metabolism. Folic acid has to go through a series of conversion steps before it becomes active. And for a significant portion of the population, more than you'd expect, those conversion steps don't happen efficiently. According to research published through the NIH, the conversion of folic acid into its usable form depends heavily on an enzyme called MTHFR. When that enzyme isn't functioning at full capacity, whether due to genetics, age, or other factors, folic acid can accumulate in the bloodstream without ever becoming what the body needs. You're supplementing. The numbers on your labs might even look acceptable, but the cells aren't getting what they came for. That gap between what you're taking and what your body can actually use is where this entire conversation lives. And the question worth carrying into the next few minutes is this: how would you even know if that gap existed in your own body? The answer starts with understanding what methylation actually is and what quietly breaks down when it doesn't work. Methylation is not a word that comes up at dinner. It's not something your doctor writes on a whiteboard during a checkup, not something that appears on a standard blood panel, not something the wellness industry has done a particularly good job of explaining without drowning it in jargon or surrounding it with products. And yet, if you were to ask a biochemist to name the single metabolic process most worth understanding after the age of 50, methylation would be a serious contender. So let's slow down and actually look at it. At its most basic, methylation is a chemical reaction. One carbon atom bonded to 3 hydrogen atoms, a methyl group, gets transferred from one molecule to another. That's the chemistry. But the consequences of that transfer, happening billions of times per day across every tissue in your body, are anything but simple. The NIH has identified more than 200 distinct biological processes that depend on methylation functioning correctly. 200! That number deserves a moment of stillness, because it means that when methylation is compromised, even partially, even subtly, the effects don't show up in one place. They ripple outward. They surface in systems that seem completely unrelated to each other, which is exactly why the connection is so easy to miss and so rarely made in a standard clinical setting. Here's a partial picture of what methylation is actually responsible for. It controls how your genes express themselves, not changing your DNA, but determining which genes get turned on and which stay silent. It synthesizes neurotransmitters, including serotonin, dopamine, and norepinephrine, the chemical messengers that regulate mood, motivation, and the ability to feel calm. It produces myelin, the protective sheath around your nerve fibers, the biological equivalent of insulation around an electrical wire. It metabolizes homocysteine, an amino acid that, when it accumulates unchecked, damages the walls of blood vessels with remarkable precision. It supports the immune system's ability to distinguish threat from normal tissue. It helps repair DNA when strands break, which happens constantly and normally, and becomes more consequential with every passing decade. The molecule that drives this entire system, the central player in the methylation cycle, is called SAMe, or S-adenosylmethionine. SAMe is the methyl donor. It's what gives the methyl group away, initiating the reactions that keep the whole cycle turning. And to produce SAMe, your body needs folate and B12 in their active methylated forms. Not folic acid, not cyanocobalamin, the synthetic form of B12 found in most inexpensive supplements. The methylated versions, methylfolate and methylcobalamin, that can enter the cycle directly, without requiring conversion steps that, for many people, simply don't happen efficiently enough. Think of it as a relay race. The baton has to be passed cleanly from one runner to the next, or the whole race falls apart. Methylated B vitamins are what allow that first handoff to happen. Without them, the relay stalls before it begins. What's particularly important for people over 50 is that the efficiency of this entire system declines with age, regardless of genetic factors. The enzymes involved work more slowly. Absorption of B12 from food decreases because the stomach produces less intrinsic factor, a protein required to pull B12 out of food and into the bloodstream. Harvard Health Publishing has noted that as many as 1 in 3 adults over 50 has some degree of B12 malabsorption, even with adequate dietary intake. The food is there, the nutrient is there, but the biological machinery to capture it has begun to slow. And then you layer genetics on top of that natural slowdown, because for a substantial portion of the population, the methylation cycle was never running at full efficiency to begin with. Not at 30, not at 40, and certainly not now. That's the piece most people don't know exists, and it starts with 4 letters that your doctor has almost certainly never mentioned. MTHFR. 4 letters that look like an acronym someone invented in a hurry. The full name is methylene tetrahydrofolate reductase, a gene that codes for an enzyme whose entire job is to convert folate into its active, usable form. One enzyme, one conversion step. And when that step is compromised, the downstream effects touch nearly everything we just covered in the methylation cycle. Here's what makes this worth your full attention. Variants of the MTHFR gene mutations that reduce how well that enzyme functions are not rare. They are not exotic. According to data from the NIH, somewhere between 40 and 60% of the general population carries at least one copy of the most common MTHFR variant, known as C677T. That means if you're sitting in a room with 4 people, the odds are strong that at least 2 of them have some degree of impaired folate conversion and have no idea. The other major variant, A1298C, is similarly prevalent. Some individuals carry variants on both copies of the gene, one inherited from each parent, which compounds the effect significantly, reducing enzyme efficiency by as much as 70% compared to someone with no variants at all. 70%. That's not a minor inefficiency. That's a system running at less than a third of its intended capacity, trying to drive a metabolic process that touches mood, cardiovascular health, cognitive function, and cellular repair simultaneously. And yet, MTHFR testing is almost never part of a standard checkup. It doesn't appear on a routine blood panel. Most primary care physicians don't order it unless a patient presents with a very specific set of circumstances, recurrent miscarriages in women, a history of blood clots, or an unusually high homocysteine level that triggers further investigation. For the average person over 50 experiencing fatigue, low mood, mild cognitive fog, or elevated cardiovascular risk, the conversation about MTHFR simply doesn't happen. Part of the answer is systemic. Standard medicine is built around treating diagnosed conditions, not investigating the upstream genetic tendencies that make those conditions more likely. MTHFR variants occupy an uncomfortable middle ground. They're not a disease, not a diagnosis, not something with a clear code that triggers an insurance-covered intervention. They're a predisposition, a tendency, a whisper rather than a shout. And whispers don't move well through a system built to respond to emergencies. Part of the answer is also educational. MTHFR research as a clinically relevant field is relatively recent. The significance of these variants for general health beyond the high-risk pregnancy context where they were first studied has only been explored seriously in the past 2 decades. Many physicians trained before this research matured, and continuing medical education doesn't always move as fast as the science beneath it. There's also a layer of controversy worth acknowledging honestly. Some researchers argue that MTHFR variants have been overstated in popular health media, and that for most carriers, the clinical impact is modest. That's a legitimate perspective, and it deserves to be said. But the counter-argument supported by a growing body of research in journals including JAMA is that the impact is not uniform, and that in combination with other factors like age, diet, medication use, and chronic stress, even a single variant can produce measurable consequences that respond meaningfully to targeted nutritional support. The controversy, in other words, is not about whether MTHFR matters, it's about how much it matters, in whom, and under what circumstances. What's not controversial is this: if your body cannot efficiently convert the folate and B12 you consume into the forms required by the methylation cycle, the consequences accumulate quietly over time. They don't announce themselves with a dramatic event. They erode slowly, consistently, in ways that are easy to attribute to aging, to stress, to the general weight of getting older. Which brings us to the question that may already be forming in the back of your mind. What does that erosion actually look like from the inside? What are the signs, the physical, daily, undramatic signs that methylation is falling short? Because some of them are almost certainly familiar. There's a particular kind of frustration that comes with feeling like something is wrong, but not being able to name it, not sick enough to stay in bed, not well enough to feel like yourself. A kind of low-grade dimming that you learn to work around, because the alternative, spending your life in waiting rooms chasing a diagnosis that never quite arrives, seems worse. That experience is more common than medicine acknowledges, and for a meaningful number of people over 50, it has a biochemical explanation that nobody has offered them. Fatigue that doesn't respond to sleep is perhaps the most consistent complaint, not the fatigue that comes from a bad night or a stressful week. That kind resolves. This is the fatigue that's there when you wake up, that coffee temporarily masks but doesn't fix, that makes you feel like you're operating through a thin layer of resistance no matter how much rest you get. When methylation is compromised, cellular energy production is affected at a fundamental level. The mitochondria, the structures inside cells responsible for generating energy, depend on methylation-related pathways to function efficiently. When those pathways are sluggish, the output drops. Not dramatically, just enough to make everything feel slightly harder than it should. Then there's what many people describe as brain fog, a mild but persistent difficulty with recall, with finding words, with holding a chain of thought from beginning to end. For people in their 50s and 60s, this is almost always attributed to normal aging, and sometimes it is. But methylation plays a direct role in the synthesis of the neurotransmitters that govern cognitive sharpness. When SAMe production is inadequate, which happens when the methylation cycle is stalled, the brain's chemical environment shifts in ways that affect clarity, processing speed, and memory consolidation. A patient in their late 50s once described it to their neurologist as feeling like their thoughts were arriving a half-second late. That half-second, day after day, adds up to something that is not nothing. Mood instability is another signal that rarely gets connected to nutritional biochemistry in a clinical setting. Irritability that arrives without obvious cause. A flatness where emotional engagement used to be. A lowered threshold for anxiety that shows up as a kind of baseline tension in the body. These experiences get labeled as depression, as hormonal changes, as the psychological weight of midlife. And sometimes that's accurate. But serotonin, dopamine, and norepinephrine, the three neurotransmitters most centrally involved in mood regulation, are all synthesized through methylation-dependent pathways. When the cycle isn't running well, the raw materials for emotional stability are simply less available. There are physical signs as well, ones that seem unrelated until you see the common thread. Tingling or numbness in the hands and feet, a symptom of myelin degradation, the protective coating around nerve fibers, that methylation helps maintain. Elevated homocysteine, which often produces no obvious symptoms at all, but silently damages blood vessel walls over years. Mouth sores that recur without clear cause. A history of anemia that doesn't fully resolve with standard iron supplementation. Slow wound healing, hair that thins faster than expected. These are not dramatic findings. They're the kind of things that get noted in passing during an annual exam, attributed to aging or stress, and never connected to each other because there's no obvious reason to connect them. The Mayo Clinic has noted that B12 deficiency alone, which can be a direct consequence of impaired methylation, can mimic symptoms of multiple sclerosis in severe cases, producing neurological findings so convincing that patients undergo extensive workups before the nutritional cause is identified. That's the extreme end of the spectrum. But it illustrates how far the ripple effect can reach when something this fundamental is running below capacity. What makes all of this particularly relevant for people over 50 is the compounding nature of the problem. The genetic variant was there all along. The enzyme was always working at reduced capacity. But for decades, a younger body compensated with greater absorption efficiency, faster cellular repair, more metabolic reserve. By the time you reach your 50s, that reserve is thinner. The compensation that once masked the problem quietly stops being enough. And there is one specific marker, a single number in your blood, that captures the cumulative damage of impaired methylation more precisely than almost any other measurement available. Most people have never had it checked. It has a name, it has a history, and understanding it may be the most actionable thing you take away from this video. In 1969, a pathologist named Kilmer McCulley made an observation that the medical establishment wasn't ready to take seriously. He was studying the arteries of children who had died young from a rare genetic disorder, a condition that caused their homocysteine levels to reach catastrophically high levels from birth. What he found in those arteries looked exactly like advanced atherosclerosis. The same plaques, the same damage, the same structural deterioration that cardiologists associated with decades of high cholesterol and poor diet. Except these were children. And the only thing clearly different about their biochemistry was that one number. It took the medical community another 2 decades to begin taking homocysteine seriously as a cardiovascular risk factor. McCulley spent years professionally marginalized for a hypothesis that has since been validated by hundreds of studies across multiple continents. That backstory matters not as a grievance, but as context for why a marker this significant still doesn't appear on your standard annual blood work. Homocysteine is an amino acid produced internally as a byproduct of metabolizing methionine, found in meat, eggs, and dairy. Under normal circumstances, it's quickly recycled through the methylation cycle, converted back into methionine or into cysteine, both useful molecules. That conversion requires methylated B12 and methylfolate as essential cofactors. When those cofactors are insufficient, or when MTHFR variants compromise the enzymes involved, homocysteine doesn't get recycled, it accumulates. And accumulated homocysteine is toxic to blood vessels in a specific, measurable way. The American Heart Association has documented the relationship extensively. Homocysteine damages the endothelium, the delicate cell layer lining blood vessel interiors, triggering inflammation, promoting plaque formation, increasing clotting tendency, and stiffening vessel walls over time. The damage is slow, cumulative, and silent, which is precisely what makes it dangerous. A person can walk around for years with homocysteine in the problematic range, feeling generally fine, while their arteries sustain the kind of wear that eventually manifests as a cardiovascular event. Most conventional labs flag values above 15 micromoles per liter as elevated. But research published in the New England Journal of Medicine suggests that optimal protection begins to erode at levels above 10, and that the relationship between homocysteine and risk is linear. There's no clean threshold below which you're fully protected. The lower, the better. within physiological limits. The cognitive angle may be even more consequential for long-term planning. The VitaCog trial, conducted through Oxford University, followed older adults with mild cognitive impairment and elevated homocysteine over 2 years. Half received high-dose B vitamins, including methylated forms. Half received placebo. Brain imaging showed the supplemented group had significantly less brain atrophy, up to 53% less in some regions. The Alzheimer's Association has since acknowledged elevated homocysteine as a modifiable risk factor for cognitive decline, one of the few where targeted nutritional intervention shows measurable effect. Modifiable means this is not inevitable. It means damage accumulating quietly over years can, in many cases, be slowed when the underlying deficiency is addressed. And yet, homocysteine testing remains absent from routine preventive care. Any physician can order it. The test is inexpensive and widely available. The reason it isn't standard is partly inertia, partly an unresolved debate about whether lowering homocysteine with B vitamins prevents cardiovascular events at the population level. What the science does support clearly is that elevated homocysteine reflects impaired methylation, and that addressing it with methylated B vitamins is safe and associated with meaningful cognitive protection. The debate is about heart attack prevention. The evidence for the brain is considerably stronger. Which brings us to the territory most uncomfortable to discuss openly, because it touches something people in their 50s and 60s fear more than a cardiovascular event. What happens to the mind when methylation has been running below capacity for years? Depression after 50 is one of the most undertreated conditions in American medicine. Not because it's invisible, it's often quite apparent to the people living with it and to those around them. But because it tends to be absorbed into the narrative of aging in a way that quietly removes it from the category of things worth investigating, you're older, life is harder, loss accumulates. Of course you feel heavy sometimes. That framing, while understandable, does real damage because it closes the door on biochemical explanations that, in a significant number of cases, are driving the experience as much as any psychological factor. The connection between methylation and mental health is not speculative. Serotonin, the neurotransmitter most associated with mood, stability, and baseline contentment, is synthesized from tryptophan, a process that requires SAMe as a cofactor. SAMe is the central product of a functioning methylation cycle. When methylation is impaired, SAMe production drops, and serotonin synthesis is reduced in a way that shifts the brain's chemical environment toward states that feel like depression, without necessarily meeting the clinical threshold for a formal diagnosis. The same pathway applies to dopamine and norepinephrine, which govern motivation, alertness, and the capacity to respond to stress with something other than paralysis. A research review in the Journal of Psychiatry and Neuroscience found that individuals with depression consistently show lower folate levels and lower SAMe activity compared to non-depressed controls, and that this holds even when dietary intake appears adequate, suggesting conversion efficiency, not consumption, is often the limiting factor. SAMe itself has been studied as a direct antidepressant in multiple clinical trials, with results comparable to standard medications in mild to moderate depression. The NIH's National Center for Complementary and Integrative Health acknowledges SAMe as having meaningful support for mood-related applications. None of this means depression is simply a nutrient deficiency or that methylated B vitamins replace psychiatric care. What it means is that for a portion of people experiencing persistent low mood, particularly those who have never responded fully to conventional treatment, the methylation pathway is a legitimate and underexplored piece of the portion cis. Picture. Anxiety presents differently but shares the same roots. When methylation is impaired, an imbalance develops between excitatory and inhibitory neurotransmitters. GABA, the brain's primary calming signal, depends on B6 in its active form, pyridoxal 5-phosphate, which is subject to the same conversion inefficiencies. The result can be a nervous system chronically tilted toward activation, not in a dramatic way, but in the low grade, always slightly on-edge way that people learn to manage as their baseline, and eventually stop questioning. Cognitive fog sits at the intersection of mood and neurology. Words arriving slower, conversations requiring more effort, the sense that the mind that was once quick is now working against a friction that wasn't there a decade ago. Research from the Alzheimer's Association has increasingly pointed to the decade between 50 and 60 as the window where metabolic and nutritional factors have their greatest influence on long-term cognitive trajectory. The damage that manifests as significant impairment in the 70s often begins accumulating silently in the 50s through elevated homocysteine, impaired methylation, and the slow degradation of myelin insulating the neural pathways responsible for clear thinking. That window is not closed for anyone watching this, but it is finite. And not everyone who needs methylated B vitamins has a genetic variant. There are other roads to the same destination. Other reasons the body may not be getting what it needs from the B vitamins already being taken. Some of those reasons may be sitting in your medicine cabinet right now. There's a tendency, once a genetic explanation enters a conversation, for everything else to fade into the background. MTHFR becomes the story, the variant becomes the villain, and people who test negative walk away feeling like this particular concern doesn't apply to them. That would be a significant mistake, because the genetic pathway is only one of several routes that lead to the same place. Age alone changes the equation for everyone. A condition called atrophic gastritis, chronic low-grade inflammation of the stomach lining, becomes increasingly common after 50, reducing intrinsic factor production, the protein that escorts B12 across the intestinal wall. Without it, dietary B12 passes through largely uncaptured. According to the NIH, this affects an estimated 10 to 30% of older adults, often without any digestive symptoms to signal it. Then there are the medications. Metformin, one of the most prescribed drugs in America, reduces B12 absorption significantly with long-term use. Research in the Archives of Internal Medicine found that depletion was dose-dependent and progressive. And the American Diabetes Association now recommends periodic B12 monitoring for patients on long-term metformin, though this is not universally implemented. Proton pump inhibitors present the same problem through a different mechanism by reducing stomach acid. They impair the step that frees B12 from food proteins before absorption can occur. A study in JAMA found that people using PPIs for more than 2 years had a 65% higher risk of B12 deficiency. For a medication millions take indefinitely, that's a consequence rarely discussed at the prescribing visit. Vegetarians and vegans carry distinct risk because B12 exists in meaningful quantities only in animal products. Liver stores can last several years, which is why deficiency often doesn't surface until depletion has been underway for a long time. For people over 50 eating plant-forward diets, supplementation is not optional. It's a nutritional necessity. The biology makes non-negotiable. What emerges is a picture more complex than simply taking your B vitamins. Genetics, age-related absorption changes, medication interactions, and dietary patterns can combine in ways that create real deficiency, even in people who believe they're well-nourished. The form of the supplement matters as much as taking one at all. The B9 in most supplements is folic acid synthetic, requiring conversion through the MTHFR enzyme. The form that enters the methylation cycle directly is L-methylfolate, also labeled 5-MTHF. For B12, most inexpensive supplements contain cyanocobalamin, a precursor requiring processing. The active form is methylcobalamin. B6 follows the same logic. Pyridoxine requires conversion, while pyridoxal 5 phosphate enters enzyme reactions immediately. A quality methylated B complex lists all three: L-methylfolate, methylcobalamin, and P5P. Those three markers together indicate a formulation built for bioavailability rather than cost efficiency. The conversation with your doctor matters, and how you enter it shapes everything. A specific, testable request works far better than a general concern. Asking to have your homocysteine checked framed as part of your cardiovascular and cognitive risk profile is a concrete ask most physicians will accommodate. A complete picture would also include serum B12, folate, and ideally methylmalonic acid, a more sensitive marker of functional B12 status that can reveal insufficiency even when standard serum B12 appears normal. These tests are inexpensive and widely available. The results create the context for a conversation that, until now, nobody has given you the language to start. There's a particular kind of impatience that comes with finally understanding a problem. You've spent years attributing symptoms to aging, to stress, to the general accumulation of life, and then a framework emerges that makes those symptoms legible, connecting them to a specific biological mechanism with a specific solution. The natural response is to want to move fast. That impulse is understandable. It's also worth slowing down, because with methylated B vitamins, more is not always better, and the path from where you are to where you want to be is more individual than any single dosing recommendation can capture. For methylfolate, doses in clinical research vary by application. For general support in individuals with MTHFR variants, 400 to 1,000 micrograms daily is commonly studied and well tolerated. The reason caution matters is specific in some individuals with certain anxiety-related patterns. High-dose methylfolate can initially worsen symptoms by depleting neurotransmitter precursors through a feedback mechanism. This is not common, but it's real. Starting low and increasing gradually is the standard recommendation. A reasonable starting point for most adults is a B complex providing 400 to 800 micrograms of methylfolate, 500 to 1,000 micrograms of methylcobalamin, and 25 to 50 milligrams of P5PA, range that supports the methylation cycle without overwhelming it. For B12, toxicity from oral supplementation is essentially unknown because excess is excreted. The relevant question is absorption. At doses above 1,000 micrograms, passive diffusion accounts for a meaningful percentage of uptake independent of intrinsic factor, which is why high-dose oral B12 can work even in individuals with impaired absorption. Sublingual formats bypass the intrinsic factor dependency entirely. For confirmed absorption issues, injectable B12 remains the most reliable option. Morning dosing with food is practical for most people. Some find evening doses interfere with sleep, likely through effects on neurotransmitter synthesis. You're deep into this video, which means you've already done what most people never do. Subscribe if you haven't yet, and share this with someone who needs it. What comes next is the part that ties everything together. What actually changes when the body finally gets what it's been missing? What should you realistically expect? Energy improvements tend to appear within 2 to 4 weeks as cellular energy production stabilizes. Mood-related changes often take 6 to 8 weeks, reflecting the time needed to shift neurotransmitter synthesis patterns meaningfully. Homocysteine reduction is typically measurable within 8 to 12 weeks, and retesting at that interval is a reasonable way to assess whether the intervention is working biochemically, regardless of how you feel subjectively. Some people notice a gradual shift, thinking that feels cleaner, energy that requires less effort, mood that is more stable without obvious cause. Others notice nothing immediately, which may mean the deficiency wasn't significant or that dose or form needs adjustment. The absence of a dramatic response is not evidence that nothing is happening. Some of the most important benefits, reduced homocysteine, slowed cognitive decline, protected vessel walls, are invisible to subjective experience, but measurable on a lab panel. The biology doesn't always announce itself. Sometimes, the most significant thing happening is the damage that isn't accumulating, the atrophy that isn't progressing, the neural pathways staying intact because the system supporting them finally has what it needs. That quiet protection, sustained over years, is what this entire conversation has been building toward. There's a moment that people describe, sometimes weeks into methylated B vitamin supplementation, sometimes months, a moment that's difficult to name precisely because it doesn't announce itself. It's not a rush of energy, not a sudden clarity, not the kind of shift you'd point to and say, "There, that's when it changed." It's subtler than that. It's the absence of something that was so consistently present you had stopped noticing it. The friction lifts. That's the closest description that holds up across different people, different symptoms, different starting points. A quality of effort that was just always there, quietly requiring less. And in that small reduction of resistance, something that had been compressed begins to have room again. This is not a promise. It is an observation drawn from clinical experience, from patient accounts collected in research settings, from the straightforward biochemistry of what happens when a system running on inadequate fuel finally receives what it needs. The methylation cycle, restored to better function, doesn't produce dramatic transformation. It produces gradual normalization, a return toward a baseline that, for many people, has been quietly receding for years without their full awareness. For some, it's sleep quality deeper and more restorative, with mornings that feel meaningfully different. Methylation supports melatonin production through a pathway running directly through SAMe. And for individuals whose sleep disruption has a neurochemical root, restoring that pathway can produce changes that years of sleep hygiene adjustments never achieved. For others, the shift is emotional, not euphoria, but stability. The return of a capacity to feel genuinely interested in things, to engage with people without the background hum of depletion, making everything slightly more effortful than it should be. For others, still, the change is cognitive, and this one tends to matter most to people who have spent years quietly grieving the sharpness they used to have. The words arrive faster. The thread of a conversation is easier to hold. The sense that thinking requires swimming through something thick begins to ease. These are not the changes of a pharmaceutical intervention. They are the changes of a body doing what it was always designed to do, no longer impeded by a deficiency it couldn't name and a medical system that wasn't looking in the right place. The Alzheimer's Association includes B vitamin status and homocysteine management among the interventions with the most promising evidence for cognitive protection. Not cure, not reversal of existing damage, but protection. The slowing of a trajectory that, left unaddressed, leads somewhere none of us want to go. The VitaCog trial's finding of up to 53% less brain atrophy in supplemented individuals is not a minor result. It is the kind of finding that, if it applied to a pharmaceutical, would be on the front page of every major newspaper. Because it applies to a nutrient unglamorous, unpatentable, available for a few dollars a month, it lives instead in a research paper that most people will never read. You've read it now, in effect. You've sat with the science, followed the pathway, understood the mechanism. That knowledge belongs to you in a way that a headline never could. There's something worth saying about the larger picture before this ends. The conversation we've had today reflects a shift happening slowly across medicine toward understanding that aging is not a uniform process, that individuals vary in ways that matter clinically, and that the difference between someone who arrives at 70 with cognition and cardiovascular health largely intact and someone who doesn't is often written not in genes alone, but in decades of small, correctable factors that either were or weren't addressed in time. You are still in time. The window between 50 and 60, where nutritional intervention has its greatest impact on long-term trajectory, is open. The question was simply whether the information reached you while it could still do its work. It has. If this video gave you something useful, a framework, a question to bring to your doctor, a reason to look more carefully at what's on your shelf, share it with 5 people in your life who are navigating the same terrain. Subscribe if you haven't already. And leave a comment telling us what you'd like us to cover next, whether that's the full science of homocysteine management, the truth about cognitive decline, or something else you've been trying to find a straight answer to.